All right. Welcome to United Astronomy Clubs of New Jersey. So I noticed there's someone just parking now. So I'll give the. Might wanna...
Got it.
We're not Darth Vader.
Well, maybe we're
Luke, I am the presenter tonight. Uh, Besides the fact, just to give them a little time to park and get down here, for those joining us in Jenny Jump State Park in Hope, New Jersey, uh, for those online, because we do live stream this to both YouTube and Twitch. So if you're ever not feeling well or can't make it out here on site, you can always check us out there during our programs. And we also keep our past programs on YouTube so that you can always go back if there was a detail you're like, man, I wish I could remember that, or you just want to check out some of the presentations that you missed. You could do that there. You can also check us out on our website, uacnj.org. That's where you're going to find a list of our member clubs, also, and a list of all our telescopes and the fun things we do to try and bring astronomy and science subjects to everyone that we possibly can. In addition, you can check us out on our social media, our Facebook, Instagram. We have a Discord channel that you can feel free to pop into and chat about your various telescopes, your astronomy questions, or even share your photos for the space photos or astrophotography. So, with that being said, for the people who have joined us now here, we do have to go over the safety briefing. It is inescapable. If you need to use the bathroom, that is the porta potty in the back. It's illuminated in red. It is to my left, your right. I also have a little museum and gift shop area that I'll be manning after the presentation. Feel free to come in and check out our display of meteorites and telescopes and other fun literature we have about our member clubs. When we go to leave, because it is quite dark, since it is cloudy and slightly drizzly, we are using our headlights because we do not like getting run over, and I am certain you feel the same. That being said, as we're wandering around, if we have any flashlights, I do ask you to keep them pointed towards the ground because we don't need to be shining those into people's eyes unnecessarily. With that, our topic tonight is about extreme EAA, which, despite what my brain tells me has to do with the aviation field, is not. It is electronically assisted astronomy, and it's brought to us by our very own Bill Murray. He's an amateur astronomer for more than 50 years, was employed as a software engineer in the Electron Optics Division of the David Sarnoff Research Center in Princeton for 18 years. More recently, he has taught high school mathematics and physics at the Trenton Catholic Academy in Hamilton, New Jersey, and has been employed as a planetarium technician at the New Jersey State Museum Planetarium in Trenton. He's a member of many different, 36-year member of AAAP. Yeah, that's enough A's. One of our member clubs, and has held posts of observatory chairman, secretary, program chairman, assistant director, and director in the club. He's been helping us out here for a long time, since 2014, and here to tell us all about the fun things he can do.
Thank you, Kim. So thank you for coming out tonight on a less than perfect night, and hopefully we can make it worth your while. So my talk this evening is about extreme EAA. Before we start talking about extreme EAA, we should talk a little bit about what EAA is, and we can do that. So if you get interested in astronomy as a hobby, everybody follows the same path pretty much. You are interested in astronomy and you think, I'd like to buy a telescope. And you get a telescope, either a relatively cheap one or a more expensive one, and start using it to look at the sky. You point it at the moon, and that's cool. You point it at the planets, and that's cool. And then what's up there else to point it at? Well, if you're like me, and like many amateur astronomers, you transition to looking at what are called deep sky objects. These are objects that are in our galaxy and outside our galaxy, things like nebulas and star clusters and other objects. And you can see a good number of those in small telescopes. But we don't happen to live in one of the better areas of our country to do astronomy from. It's pretty tough to do astronomy in New Jersey. And so after a while, after seeing maybe a few dozen of these objects, and they all relatively look the same, you ask yourself, well, how do I improve my view? What else can I do? And one answer to that question is something called EAA, which stands for Electronically Assisted Astronomy. So if you're interested in doing EAA, what do you need? First up, it's a type of astronomy, an astroimaging that's done in near real time, which means the image comes up in just a few minutes, okay, rather than hours. So you can see it as you're doing it. And you need three things. You need a telescope that tracks the stars. If it's a go-to telescope that knows where things are in the sky and can point to them, that's a plus. You need a CMOS astro camera. There are many of them out there, and they run price range from several hundred to several $1,000s. If you're starting in the hobby, you're probably going to start with one maybe in the several $100 range. And the last is an app that does live stacking. We're going to talk about each of these components. So there's actually a continuum between visual observing and EAA. The ethos behind EAA, electronically assisted astronomy, is you're basically just replacing your eyepiece with a camera. And instead of looking through the eyepiece, you're looking at a monitor to see the image. The advantage is you can see a lot more with cameras than you can with your eye. Okay? Cameras can integrate an image and add up the light that it receives over many minutes, whereas your eye just gets the light that's coming in a fraction of a second. And so the image that you will see on your monitor is going to be much brighter, much more detailed, show you a lot more. Okay. So the components that you need: a tracking telescope. You don't have to have an equatorial mount. There's two different types of mounts basically for amateur astronomy telescopes. There's equatorial mounts, which track the motion of the Earth through the sky, okay, by aligning themselves with the pole, and then they track the Earth simply by rotating one axis. And there's also Altaz telescopes. Now, modern Altaz telescopes can also track the sky, but they have to do it with two axes. A little bit more difficult to do. Telescope does not need to be large. Just a few inches will be enough. And polar alignment is not required. If you have an Altaz mount, you can just set it up and then align the mount. As long as it's tracking the object that you're pointed at, that's fine. There's many models in different price ranges around for people who are interested. So the next thing that you need is a CMOS camera. CMOS stands for complementary metal oxide semiconductor. These are the newer versions of astro cameras that have come out over the last 10 years or so. Much better than previous digital cameras that were used. The main reason is there's much less noise, either both thermal noise and read noise. So it used to be with astronomy cameras, which were called CCD, charge coupled device cameras, that you could take an image through them, but when that image was downloaded to a computer, there was a bunch of random noise that got added to that image, and that was called read noise. And the read noise tended to be relatively large. So what you would do with those cameras is you take as long as an exposure as you could, 5 to 10 minutes or so, and then take another one and add it to it. The reason why you wanted long exposures is because you wouldn't have very much read noise to deal with. Okay, but that meant that was a constraint on your telescope, because then the telescope has to track very accurately over that time period, and made it a lot more difficult to do astroimaging. Nowadays, there's virtually no read noise in CMOS cameras. And so you can take 30-second, 15-second, 5-second exposures and add them up one after another without any of that noise being added. And that makes it much easier on the telescope to track objects. Okay? And again, there's many different models around of these type of cameras. And the third thing you need is an app on your computer that will do what is called live stacking. So what this app does is it reads the image from your camera and then waits until another image comes down, and it will take that image and will align the stars in that image with the previous one, and then just keep adding them up as you take more and more images. And that allows you to increase the density in your image and show a lot more detail. These are two apps that I've used, and they're pretty common. This one is called SharpCap. I use this when I'm doing imaging in my observatory. And the other one is called ASI Live, which is put out by the ZWO company. ZWO is one of the major camera manufacturers, and this is their software that comes with their cameras for doing live stacking. So, as I said, what this software does is it takes the image that comes from your computer and keeps adding it up continuously as your camera keeps stacking. It aligns the stars so that the images are aligned. It doesn't care whether the image is 2 minutes long or 5 seconds long. It'll keep doing it. And as time goes on and you get more and more images, you'll see more and more detail coming out. And usually with just standard EAA, within about a minute or so, you can see an image on your screen that's better than anything you will see through even very large telescopes, which makes it very interesting to look at. You can also get all-in-one systems like this here. This is a little Raspberry Pi computer called ASI Air, and it controls everything in this process. It controls your telescope mount, it controls your camera, and it makes both of them go to an app on your iPhone or your iPad to actually image, so you don't even have to have a computer to do it. So some of the characteristics of the EAA experience. Lots of detail and color. That's usually invisible in small and medium scopes. That makes it a scope multiplier. So I've looked through a lot of telescopes. I've been an amateur astronomer for over 50 years, as my bio said. I started back in the 1960s during the space age. I was one of those kids who got fascinated by the space race back then. And I've been doing astronomy pretty much ever since. I've looked through telescopes that are 2 inches in diameter. I've looked through telescopes that are 25 inches in diameter. And the detail in the images that I can get with my telescope set up using EAA, I can see more detail in those images than I ever saw on a 25-inch telescope, which is amazing when you think about it. So this is a real scope multiplier. It allows you to see much deeper than you otherwise would. You can view the image in real time, so it feels more like actual visual observing. So usually when you're doing standard EAA, the image will come up in a minute or two. Okay. Shorter integrations, shorter exposures mean you can go to a bunch of different images. So if you look at one thing for a couple of minutes, then move the telescope and look at another object for a few more minutes, you can see a lot of stuff in a single night. It's relatively easy to use for astronomy imaging setups. Basically, all you need is a telescope, a camera, and a computer. Okay? And it can't compete, the image quality that you get can't compete with long exposure astroimaging. It wasn't designed to do that. It was designed to show you as much detail in a short amount of time as possible. And we'll go into a little bit about what is required for long exposure astroimaging, what the difference is between that and EAA, and how they can mesh together. Okay? And lastly, it's great for outreach because it allows you to see the image on a monitor, makes it easy to see, easy to explain, and more than one person can see it at a single time rather than everybody looking individually through the eyepiece of a telescope. Okay. So how about long exposure astroimaging? You might think that they're similar, but there are quite a few differences. So this is a picture of a telescope set up for imaging objects over periods of hours or perhaps even days. It's not uncommon that people who do astrophotography will image one object all night, leave their telescope set up, come back and image it again the second night, or maybe even a third night, because they're trying to require as much data as possible. To do that, you require a lot of these things. So you need precise polar alignment. So this is an equatorial mount that's been polar aligned. You have to guide the image. There are many accurate telescope mounts, but no telescope mount is accurate enough to track the stars for very long by itself. So what astronomers do is they'll take a second telescope, called a guide telescope, with its own camera. And the purpose of that telescope is just to take an image of the stars, and then a few seconds later, take another image, and it will see the tiny amount that those stars move due to the misalignments in the mount, and it will send commands to the mount to correct for that, and continually does that all the time while you're imaging. Okay, that way the images will be aligned, and you won't have to worry about drifting or there being star trails or other effects. Okay. Calibration frames, we'll talk about that in a minute. A must if you're doing long exposure astro imaging. Said integrations of several hours or days. You may use various filters to isolate various wavelengths of light in your image and combine them with. And then after all that is done, you have to take the images that you get and process them in a computer, and that process can take sometimes as long as acquiring all the data did. So this is not a short procedure. So the characteristics of astro imaging. No question, you could get superb images this way. The images that amateurs are taking these days knock the socks off of the stuff that professionals were doing 30, 40 years ago. Much, much better. The integrations of several hours means usually you only target one object per night, maybe two, but not much more than that, because you're trying to acquire as much data on that object as possible. As you can see from the previous images, it's complicated. There's a lot of moving parts that you have to keep track of. Not good for outreach. Okay, you just set up the telescope, program it to take the images, and then a lot of the people who do this, they'll have it all automated. They'll just go, and they'll do something else for the rest of the night while the telescopes takes images all night long. And the image post-processing, in many cases, takes as long or longer than the actual acquiring the images did. But just like there is a continuum between visual observing and EAA, there's also a continuum between AAA and astro imaging. So as I described EAA before, that's a basic setup for EAA. But you can, since this is EAA, and my definition of extreme EAA, and a lot of these are subjective, I'm making up my own definitions here, is I'm starting to use some of the techniques from long exposure astro imaging to increase the image quality in the EAA images that I'm getting. Okay? So my definition of extreme EAA is I'm going to use some of those techniques that astrophotographers use to enhance the image quality while still trying to keep the experience as live as possible. Okay? But there's a danger here. The danger is that you actually tip over the scale and move into long exposure astro imaging instead of doing EAA. Mark, who's one of our EAA gurus here at UACNJ, calls that moving over to the dark side. You always have to keep in mind when you're doing extreme EAA not to go too far. So in my definition, what constitutes extreme EAA? Accurate polar alignment, accurate focus, guiding, target location using plate solving, calibration frames, longer subframes. In EAA, typically subframes will be like 15 to 30 seconds. In extreme EAA, that can go up to about a minute. Longer total integration time. I try to cap it at about 30 minutes because that's kind of like the limit that most people will stick around to view one object before we move on to a next one. So I try to keep the total exposure time for any image under a half hour. and using aggressive stretching of the image in real time. And we'll talk about all of these. And again, all of these definitions that I've used here are subjective. They're things that I do, and I think a few other people are doing, to enhance image quality in EAA. It used to be that many of these things were relatively difficult to do. So if you did astrophotography, what you would do is you'd have a permanent setup in an observatory, and you'd set up your mount and polar align and do a lot of these things prior to doing any imaging, and then you would leave that setup there and not change it. Okay. In many cases, many of these things like polar alignment could take several hours. Thankfully, nowadays, many of these have become much easier to do, and we're going to talk about some of the ways that they are easier. So the first up is polar alignment. Okay. It used to be that you would do something called the drift method, which was very tedious. You'd set up an equatorial mount and aim it at the pole roughly, and then you would turn it on and track a star for a few minutes and watch which way the star moved off of the crosshair in your eyepiece. And then, knowing which way it moved, you'd make some small correction to the mount. And then you'd do it again, and then you'd do it again, and then you'd switch where you were looking in the sky and make adjustments to the other axis. It was not uncommon that getting good polar alignment this way could take several hours. Okay. Nowadays, they make devices like these polar alignment cameras, which are mounted in telescope mounts, and basically the camera does all the work for you. So it'll take a picture of the stars near the pole where your mount is pointed, and then it will turn the mount a little bit, take another picture, and say, okay, this is how far off you are. Move this way, move that way. You make the correction, it does it again. Okay, you came a lot closer, do it again. And then the second or third time, you're done. You have polar alignment within about less than 5 minutes. And it's much, much more accurate than you ever got polar alignment with the drift method. So that is a big time saver nowadays. Focus. There are a variety of methods. The one that I use is something called a batten-off mast, which is a piece of plastic with slots cut in it. And this is an example here of what it looks like. So when you want to focus your telescope, you take this piece of plastic and put it over the front aperture of your telescope. What that does when you take a picture of a star is it creates a diffraction pattern. Okay? So you get two diffraction spikes in the form of an X, and then a third spike that's vertical with respect to those. If you're inside focus, the central spike will be a little bit off to the left. If you're outside focus, it'll be a little bit off to the right. And when you're exactly in focus, it will exactly bisect the cross. This is extremely easy to see and very, very sensitive. So you can adjust the focus on your telescope, take an image for a couple of seconds, see one of these patterns, and say, okay, I got to turn it the other way a little bit. And then within just a couple of minutes, you can have very, very accurate focus on your telescope. Then you take the mask off the telescope and go and do your imaging. Okay. Guiding. Okay. Again, I'm old enough and I've been in this hobby long enough that it used to be that when you were auto-guiding, that meant something that the observer had to do. So there was a guide telescope with a little eyepiece in it, and when you wanted to do astro imaging, you would look through that telescope the whole time that you were imaging and use fine motion controls on your telescope to keep a star centered in the crosshair. We don't do that anymore. So nowadays, the two main ways you guide is with a guide camera, which is a small telescope and camera combination that's attached to your main telescope. Okay. Another way to do it is with what's called an off-axis guider. So this is a little pick-off mirror in here that picks off some of the light that's going to the main camera right here, goes to a guide camera. Okay. My preference is actually using a guide telescope. You tend to get a much wider field and a more robust selection of stars to guide from. And then we now have guiding software that does all the work for you. The most common guiding software that people use is called PhD2. That stands for push here dummy, because once you do a little bit of setup with your camera and your telescope, you basically say, okay, you push this button and the software will take over and it will guide your image for as long as you want, for hours if you want, okay? And give you a graph that shows you how well it's guiding. So the red and blue are the motions in right ascension and declination, and as long as they stay relatively close to the center line, your guiding is good. So you can monitor it as you're imaging. Plate solving, which is pretty new. It's only come out in the last, I'd say, 5 years or so. It used to be when you were trying to find an object in the nighttime sky, especially if you can't look through the telescope because there's a camera attached to it. You would take an image, you have your telescope move to the object, take an image, okay, it's not there. Okay, well, which way do I have to move the telescope? And you try some things and move it one way, and then try some things and move it another way. Eventually, a lot of times I'd have to go back to my telescope. I tend to do my imaging from inside my house. And use like a finder scope on the telescope to find the object, and it was a very painful experience. What this plate solving software does is it keeps a model of the sky with the positions of several million stars throughout the sky in it. And when you activate it, you take an image of the night sky and you say, okay, I'm pointed at M13, which is a globular cluster in the Hercules. We'll talk about that again in just a minute. And the plate solving software said, oh, you thought you were pointed here, but you're actually pointed here, because it takes a picture of the sky, checks it with its model, and in just a couple of seconds says, okay, you were off this much. And then it says, okay, I'm going to move the telescope back to where you thought you were. And so within 10 seconds, the object that you were looking at is directly in the center of your image, automatically every time. It's like magic. It's amazing. And that works especially well if the thing that you're trying to image is so dim you actually can't see it in the image. You can use this plate solving software to center it and have a very good assurance that it's actually centered in your image even if you can't see it. So calibration frames, okay? So what are calibration frames? The cameras that we use for astro imaging are very good, but they're not perfect, and they have some defects. And so you need to take what are called calibration frames, which are specialized images that you take before imaging to correct some of those defects. And the two main type of calibration frames that people use are shown here. This one on the left is called a thermal or dark frame, and this one is called a flat frame. Okay, so let's talk a little bit about each of them. So dark frames. The cameras that we use for astro imaging are very sensitive. They can pick up very faint light, but most, if not all of them, are also sensitive to infrared light. And infrared light is heat. So what a lot of manufacturers of these cameras do, they'll take the camera and put a cooler behind it, so it'll take the temperature of the camera down to 10-20 degrees below 0 Fahrenheit. But that still doesn't get rid of all of the thermal noise. So what you would do to get rid of the rest of it is take an image with the lens cap on your camera. So it's taking an image of nothing but darkness for the same amount of time and with the same gain as you would take your normal image. So if you're going to take subframes that are a minute long, you take a bunch of these dark frames that were also a minute long. Okay? Add them all up, you take a dozen or so of them, and then that dark frame gets subtracted from every image frame, and that will get rid of all of the rest of the thermal noise in your image. Okay. Even more insidious is effects called vignetting and dust donuts. So this is an example of a flat field frame. So how do you take these frames? Well, you take your telescope when it's in focus and point it at a uniform light source, okay? A completely flat white light. And if you do that, you'll get an image that looks like this. You would expect it to be just uniformly white, but it is not, because the lens in your telescope is going to have more light at the center of the image than on the edges. That effect is called vignetting. Okay? Virtually all optical systems have it to one degree or another. These little things that look like donuts, okay, are actually specks of dust somewhere on your imaging system. Could be on the lens, could be on an interior lens, could be on the window of your camera, could be on the sensor of your camera. Somewhere in the optical train where light is coming through, there's one of these little particles of dust, and it's out of focus because it's not at the same position that your camera is, and you get one of these dust donuts. Okay? The reason why these things are so bad is when you try to enhance your image after you've taken it, we'll do something called stretching, and I'll talk about that in a little bit. Basically, you're taking the image and the position, the amount of light in a certain area of the frame where the image is, and you're making it brighter. Okay, but when you do that, you also increase the brightness of these things. Okay, so it's much better to get rid of them rather than try to enhance them. Okay, and flat frames will do that. So you take a series of flat frames also before you image, and then divide your image by that, and that will get rid of all of these effects. Okay, and that will allow you to stretch your image much more than you would have otherwise. Okay, so here's an example of an image that I took, and it's a picture of a galaxy. Okay, and I'm trying to stretch the image, but when I do, you can see there's vignetting coming in and dust donuts as well. So I can only stretch it so far. Okay, and that's the advantage of using flat frames to get rid of these effects first. It'll allow you to stretch the image much more than you could otherwise. So how do I do imaging? Okay, I have a variety of setups, but the main one I use is I have an observatory in my backyard. Okay, so this is my observatory. About 15 years ago, my wife and I decided we were going to put in a deck and patio in our backyard, and I said, oh, by the way, if we're going to do that, I want to do this as well. So we put in a little walkway to a side patio, and I got an observatory kit. This is a 6-foot home dome, and I've had that in my backyard now for more than 10 years. This is my original EAA setup. So I've got a 5-inch telescope. It's an astrophysics refractor on a Lost Mandy mount. My original camera was an Attic Infinity. It was a black and white camera only. And so that's your basic EAA setup. You've got a telescope with a mount and a camera connected to a computer that has EAA software on it. So here are some of my early results when I just started out doing EAA. And the fact that they look as good as they do points to the fact that EAA is a very powerful tool for astronomers. So this is Messier 13, the Hercules cluster, the Great Globular Cluster in Hercules, a group of about 500,000 to 1 million stars, very old stars in our galaxy. And one of the brighter globular clusters. There are about 150 of these globular clusters that orbit around the center of our galaxy. NGC 4565, the Needle Galaxy, one of the more spectacular edge-on galaxies that we can see. This is M27, the Dumbbell Nebula. This is a planetary nebula. It doesn't have anything to do with planets. It's what's going to happen to our sun in several billion years when it runs out of fuel. It will become a red giant and expand out, and most of the gas in our sun will expand out and form one of these clouds called a planetary nebula. This is M17, the Swan Nebula. Unlike the previous nebula, this is a place where stars are being born. So these gas clouds exist in our galaxy, and every once in a while some area of the cloud will become a little bit denser than other areas of the cloud, and when that happens, they'll begin to compress, and as they do that, their gravity increases and they begin to pull in more gas from the rest of the cloud. Eventually, those areas of condensations become so hot and dense that nuclear reactions start and stars are born. So you can see some of the very young stars being born out of this nebula right now. Eventually, as this happens, the radiation from the stars will blow away the remaining gas, and you'll be left with what's called an open cluster. A cluster of several hundred to several thousand very young stars. So my early efforts in EAA, I was very pleased with the images. The image quality was good, but I felt it could be better. And so I started upgrading my equipment. Okay, so this is the setup that I use currently in my observatory. Same telescope. I've got an astrophysics mount now, which is a bit of a better mount. This is my new astronomy camera, which is a CMOS camera. There's my guide telescope. I'll take a look at each of these in detail. So I have an electronic focuser on my telescope. So it has the nice options that I can either focus manually, I can focus using my computer in the observatory, or I can focus with my computer in a remote location. I have all three options I can use with this focuser. So I can actually focus the telescope remotely. I have a batten-off mask, okay? And as I said, what I like to do is to keep my telescope in the observatory and sit in my living room and do my imaging from in there. Well, batten-off mask, you have to put on the telescope, focus the telescope, and then take it off the telescope. Well, I'm lazy. I've been in this hobby long enough, and the longer I'm in it, the lazier I get. So I was looking for an option to take care of that, and I found this one, which is an Alnatech flip mask, which again has a remote toggle with it. So when you toggle it on, it will take the mask and put it in front of the telescope. You can focus the telescope until you're satisfied, and then you hit the toggle again. Oops, sorry, didn't mean to do that. Oop. Yeah, that'll work. Yeah. Then you hit the toggle again, and it will move the mask away from the telescope. So you can do all of that remotely as well. I also have what's called a Taurus 2 tracker, which is how I mount my camera. This is my old EAA camera, the Alnatech, or the Attic Infinity camera. The nice thing about this is that it has a guide port. It's actually an off-axis guider, but it also has a viewport. So you have you can put an eyepiece into it and use the telescope visually without removing the camera from the telescope, which is kind of nice at times. My guide scope on top of the telescope, an Orion 60mm guide scope with Starlight Express guide camera on it. Very securely mounted to the telescope, so I don't have to worry about any flexure. Okay. And then what I do for flat fields. Okay. So I made my own flat panel. It was actually a lot simpler than I thought it would be, but it's a little bit of a job. So here are some of the components in it. It uses a dimmable Artcraft Lightbox tracer. I use some neutral density filter, black foam core board, gaffer's tape, and binder clips. So I put the neutral density filter over the Lightbox and then put black foam core board around it because I wanted to suppress all the light except the light that I wanted, and use binder clips to attach various of my masks to it, depending on which telescope system I'm using. So here's an example of how it works. So it's also electric. It can be powered through a USB cable, which is nice because I have lots of USB ports on my telescope that I can plug it into, which makes it very simple. You turn it on, and you get a flat field, and it has adjustable light, so you can adjust the brightness of that to make it brighter or dimmer. So when I want to take flat frames with my telescope, what I'll do is take this, go out, put it on the telescope. My software has set up, I can just hit it and it'll take 20 or 30 flat frames. And then when I'm done with that, I just take this off the telescope and put it away, and I'm done. It takes about 2 minutes. I also have a variety of other masks of various apertures for other systems, so I can use it with the same flat panel. So this is kind of a schematic of the way my observatory is set up. So I've got my telescope, camera, the mount, and the focuser. What's not shown here is the guide camera that's also connected in. I have them connected to a USB extender in my observatory. I run a wired Ethernet cable into my house where there's a sender which is attached to my computer. And the computer actually acts as if all these USB connections were connected right into it. So it's like the computer was sitting inside the observatory. I tried doing wireless for a number of years, and it never worked. I tried a variety of different things. The connections were always brittle. They would drop. There was a lot of noise. They were slow. Eventually, I went to an Ethernet cable, and all of those problems disappeared. So probably the next thing that I will do is I'll have a hardened Ethernet cable buried in my backyard to go from my house to my observatory. Right now, I just string one up when I need it. So this is a little bit of an overview of the workflow I do when I'm imaging. So I run the Ethernet cable between my dome and my house. I turn on the mount, the camera, connect to the computer, turn on the camera cooling. If I need them, I can take dark frames. When it gets dark enough to see the stars, I focus my telescope. Then I take my flat frames. When it's dark, all of the twilight has vanished from the sky. I slew to a target and I plate solve, select a guide star, begin guiding, start live stacking, and then just watch the images come down for however long I want. I can adjust the color balance and stretch as the data is accumulating. When I'm happy with it, I'll save it, go on to the next target. So some examples of some of the images I've done more recently. So this is one of those open clusters I talked about, M35 in the constellation of Gemini. That's located right here. This was 13 60-second frames, so a total of 13 minutes of exposure. And also in this image is a much more distant open cluster, NGC 2138, which is much richer but much farther away than M35 is. So this is the galaxy NGC 4216, located right here in the Virgo cluster of galaxies, along with some satellite trails in there as well. Thank you, Elon Musk. He's the one who's causing most of these days. The fascinating thing about this image is the Virgo cluster is the nearest supercluster of galaxies that we have, and in just a few minutes you can capture a lot of galaxies. In this one image, there's, I believe, 14 or 15 easily visible galaxies. So you got these three edge-on galaxies here, but you also have one here, one here, one here, one here, one there, one there, one there, one there, one there. They're just all over the place. Okay. So in just a couple of minutes, this camera can capture very dim galaxies. Okay. You wouldn't be able to see any of these galaxies visually in a telescope, but the camera can capture them pretty easily. Okay. Also, close-up view, a lot of detail starts to become visible in some of these galaxies. So with just a small camera and a small telescope, you can start doing studies of the different structures of galaxies. Another galaxy in Virgo, Messier 98. This is 30 60-second frames, so a half hour of exposure. And again, quite a bit of detail in there. This is the famed Whirlpool Galaxy, Messier 101, 30, 60-second frames, so again, a half hour. This was taken last year, okay? And as many people know, earlier this year in February, there was a supernova that went off in this galaxy. About 5 days after the supernova was discovered, I decided to see if I could get an image of it. It was a terrible night. Basically, I went out and looked up, and there were only 3 or 4 stars visible, cloudy and hazy. I said, "Oh, I'll see what I can do." And so, surprisingly, I got an image here that looks reasonably good. So, supernova, right there. Now you see it, now you don't. So this is pre-supernova, and there's the star that exploded right there. NGC 891, 30-second frames, so 15 minutes. One of the better edge-on galaxies in the fall sky. It's in the constellation of Andromeda. NGC 2392, also a planetary nebula in the constellation of Gemini, known as the Clown Face Nebula. And the nice thing about this system is that you can zoom in quite a bit. And if you do that, you can even start to see some detail in the clown face, the brighter central region, some of the details in the nebula. NGC 4565, the Needle Galaxy, which I showed before. 33 60-second frames, so 33 minutes total exposure. The interesting thing about this one to me is you zoom in a bit. So there's a lot of detail in the galaxy, but then you've got all of these faint galaxies. And these 2 guys here, I actually went to catalogs and checked them up. They're magnitude 16 and 17 galaxies. So in a half hour, you can get images of galaxies down to 17th magnitude, which is pretty impressive for a 5-inch telescope. If you had a 30-inch telescope and you were looking through it, you would never see these. But you can get them with imaging. NGC 2903, which is a nice barred spiral galaxy in the constellation of Leo. Again, a lot of detail visible here in my image. Everybody's favorite, M42, the Great Nebula in Orion, along with M43 and Sharpless 279, the Running Man Nebula over here. 23 30-second frames, so about 11.5 minutes to get this image. M81 and M82, Bodes Nebula in Ursa Major, 2 bright galaxies, and again, quite a bit of detail in the galaxy visible in that image. And lastly, M13, what we started off with, as well as the faint 12th magnitude galaxy NGC 6207, 23 30-second frames. So again, 11.5 minutes. So sometimes I go over the line and veer a little bit into the dark side. I tend to take longer exposures, do some special techniques with them. So this is M1, the Crab Nebula in Taurus, 148 30-second frames. And when you zoom in, you can actually start to see some of the gas tendrils in the image, which is what Lord Ross discovered with his 48-inch telescope back in the 19th century visually, and allowed him to give this object the name the Crab Nebula, because it looked like a crab to him in his telescope. And M27, the Dumbbell Nebula, 51 60-second frames with a lot of very faint detail visible in the image. Okay. I don't only use my observatory. During the summer, I was up in the Adirondacks at the Adirondack Astronomy Retreat, and I did some EAA with a 35 millimeter camera with a 135 millimeter lens attached to it. So this is an image of the Sagittarius star cloud. So this is the Lagoon Nebula, M8, the Trifid Nebula, M20, the small Sagittarius star cloud, M24. Just above that, so here again is M24, is M17, the Swan Nebula, and M16, the Eagle Nebula. This is the bright star Altair in the constellation of Aquila the Eagle, and the dark nebula called Barnard's E, right there. So that's dark gas sitting in front of the stars that are blocking the view of the stars behind it. The Elephant Trunk Nebula in Cepheus, the elephant trunk being right there. The entire constellation of Lyra, the bright star Vega, Epsilon Lyrae, the double-double star, as well as the 4 stars in the parallelogram that make up the constellation. And zooming in right in the middle between these two, it's faint, but it's there, is the Ring Nebula, M57, another planetary nebula. And lastly, the Cocoon Nebula in Cygnus, along with a dark dust trail that moves away from it. Well, that's my talk. Hopefully everybody found it enjoyable. And if anybody has any questions, I'd be happy to try to answer them for you.
All right. Thank you, Bill. Thank you for people who have joined us here and online. So, how question and answer session works is for if you're here, you'll raise your hand and keep that up until I bring the mic to you, because chances are if you have that question, someone else online or here has the same and might not be brave enough to answer that. Brief safety briefing in you have the porta potty if you need to use the restroom. Afterwards, we do have the museum and gift shop area. Unfortunately, we have not opened any telescope observatories tonight because it was quite rainy earlier and it is still quite overcast. Right, so to start things off, the first online question I see is, how good is EAA at cutting through light pollution for those of us that live in urban areas?
So one of the nice things about EAA is because cameras are so sensitive and you can get so deep relatively quickly, it's pretty easy to use light pollution filters. So you can cut out a lot of light pollution. But even without using light pollution filters, I live in Bordentown, New Jersey, which is like a Bortle 6 sky, which is, better than the center city, but not great. It's a bright suburb. And I do most of my stuff without light pollution filters. So basically all of the pictures that you saw were done from a fairly light polluted suburb.
All right, do we have a question out here? Perfect.
Hi, how far away are the nebulas from us?
So the nebulas range, they're in our galaxy, so they range from several thousand to several tens of thousands of light years away. The galaxies that I showed are on the order of 50 to 60 million light years away.
All right, so our next online question, which do you prefer, visual observing, EAA, or astrophotography?
So I do all three. Visual observing is great, especially if you can get to a dark sky. So I have a relatively large telescope, so I do visual. I haven't completely gone over to the dark side yet. But I do a lot of EAA because simply from my backyard, I can see a lot more with that than I can. And I'm starting to get into long exposure astroimaging too.
All right, is there another question out here?
I'm sorry, Bill, what is your favorite type of object to see through EAA? For instance, I find galaxies wonderful with the EAA. What's your favorite type of object?
So my favorite actually is galaxies. Okay, if you take a look at, for instance, the NGC catalog, probably 90% of those are galaxies. So it's definitely the major component of things that you can look at, and they all have different structures. And the nice thing about EAA is you can actually pull out a lot of that structure in your images.
All right. So our next online question is, can you use a cell phone to do EAA? Like have the video of the phone be looking through where the eyepiece would be?
The answer to that is yes. So I showed earlier when I was talking about the equipment for doing live stacking. There's this little device that's made by ZWO, and it's not the only one. There are other companies that make similar devices called ASI Air. And so that controls the telescope, the camera, all your equipment, but it's run by an app that can either be on your iPhone or your iPad. So when you're doing EAA, the actual app is on your iPhone, and the image accumulates there. So you can walk around with your iPhone and to watch the images it accumulates using live stacking.
Yeah, I think from the phrasing, I think they were talking about using the phone's camera to be doing that.
You can use iPhones for astro imaging. Usually it's large field astro imaging. So if you want to take a picture of the Milky Way, you can put your iPhone on a tripod, and there are various websites that'll tell you how to do that. So yes, it is possible.
All right. Was there another question out here? Perfect.
So when you said you filmed the supernova happening in real time, was that actually in real time, or was it because it's so far away, like millions of years ago?
So M101 is, I believe, on the order of like 50 or 60 million light years away. So that's when the supernova happened. But it took that long for its light to reach the Earth. And so the image that I took was 5 days after the discovery was made that the supernova had gone off. About 50 million years after it actually went off.
Yeah, unfortunately, it's not like that gaming computer. It's the lag's a bit much on that one. All right, so our next online question. Do you have problems with bringing things into focus for other people because you wear glasses? And they give an example. If they adjusted focus for their eyes, it might not be in focus for someone else. And if they're wearing the glasses, they have the same but slightly different trouble. Are there any hints if you do?
So I think that's a pretty common problem. I tend not to wear my glasses when I'm doing visual observing, and so I focus the telescope for my eyes. But when I have someone else look through my telescope, I'm always aware that it's probably a bit out of focus for them, so I show them how to do focus for themselves. That's one of the advantages of EAA, is the focus is standard for everybody. Everybody sees the same image whether they're wearing the glasses or not. So you don't have to worry about your telescope being in focus for one person but not being in focus for another person.
All right. So another online question is, do you feel like you have enough room to move around your scope in your tiny dome?
No. So I used to actually sit in there when I was doing EAA, but it's very cramped, and so that encouraged me to completely automate the setup as much as possible, so that I can sit in my nice, comfortable living room to do the imaging rather than in a chilly, bug-infested observatory.
There's a reason why we just bug spray to everyone who does this. Another question here. All right, so I have like 3 more questions online. So if you guys online have any other questions, do get those in so we can get them answered. Our next online question is actually more of a statement, and it's about the next question. Is the mask flipper was something you could buy ready-made and already set up?
The flip mask, yes, the flip mask is a commercially available product. You have to tell them what the size of your telescope is, of course, but yes, you can buy it.
and the witty comment was they're envisioning another person made a comment off of that, where they were envisioning a person with a Lego set, a Raspberry Pi, and a lot of ambition doing a DIY version of that.
Always possible.
Who has that many Legos? All right. Any questions? All right. So if you have any questions, just kind of raise your hand and wave them about. So I'll just get through these last few online questions. Can you take your flat frames at the same time as your dark frames, or is there a reason why you take the flats when you do, which is after the focus stage?
So in order to correctly correct for the effects for flat fields, you do have to have the telescope in focus. And normally when you start out, you don't have the telescope in focus. And how do you focus a telescope? Well, you have to focus on a star. So what I usually do is, while it's getting dark, but before it's completely dark, since the telescope would be covered anyway, that's when I take the dark frames. And then after it gets dark enough to see a star and I can focus my telescope, that's when I take the flat field frames.
Neat. And our last online question so far is, do you have problems adjusting the public expectations between what you can see in an astrophoto, like in the magazines, versus than what you can see in EAA and what you can see visually?
So it always is a bit of a disappointment for people to see objects visually, because they have expectations from pictures that they see in magazines. People do like to look through telescopes, though, and so there's always going to be that aspect of it. You can have a whole bunch of different monitors. Down at my club, at the Amateur Astronomers Association of Princeton, we actually do EAA on one of our telescopes for the public during our public nights, but we also have eyepieces on the same telescope, so you can actually view the object visually or look at the monitor, your choice.
All right. Also, based on that, is there anything specific you might say to temper their expectations, or like?
So we always tell them it's not going to look like what you see the pictures look like, and explain to them why. It's that the human eye is not really good at seeing dim light, but cameras are.
Oddly enough, the robots have us there. Right, any last minute questions here? Right, so I want to thank everyone who's, like I said, who's joined us both here in Jenny Jump State Park and online. Do check us out on our website, uacnj.org, for a list of our upcoming talks and all the fun information you could ever want about it. Thank you, Bill, for another great presentation, and everyone have a good night.
Thank you.